In this video, I'll replicate my paper with Fabian Mandel on control variables using Positron and Claude Code. I've done a similar replication in the past using Claude 3.7 and Klein coding assistant with Visual Studio Code. But this is a more advanced implementation of the same demo. So we are like half a year of AI development, and also I have a new editor. So this editor here, it's Positron. So it's an R editor, R and Python editor from the same company that makes RStudio. And this is their next generation product. So we can see that there's something similar to RStudio, like we have variables here, plots here, and then there's R console or terminal here. And but then this left-hand side here shows that this is actually built on Visual Studio or Visual Studio Code. And that means that all the coding agents that are available for Visual Studio Code are also available for this product. And I will replicate the paper, and I'm pretty sure that this will be replicated perfectly with a little bit of prompting. So I've tried this once before, earlier today, and I almost got it to work with just a single prompt. And now that I know what the model has problems with, I'm pretty sure that I can just make it work. So our task is we are trying to replicate this plot here. And what we are doing here is we have the folder. So I have this folder, it's called demo, it's on my desktop. And I just give the coding agent the PDF. And then I will not touch the code myself. I'll just tell it to read the PDF and replicate the paper. So we are going to be using Claude Code version 2, and it opens here, so we don't need to have that open anymore. And what we'll do next is that we will tell it, we will give it a prompt, and we want to make sure that it's in planning mode, because the model first needs to come up with a plan that improves the quality of the code and the solution. So we just tell that we want to replicate the figure 4 from the paper and replicate the simulation number 1 and use R. And we'll have it read the PDF. So this is a multimodal model, which means that it can understand text and image input. And what makes this replication really hard for earlier version of Claude is that some of these details about the simulation is only available in this figure here. So these equations that are here are not available in the actual text. And when I replicated the paper before with Claude 3.7 using Klein coding agent, I had to tell it what these equations are, just type them in. And now it's looking for the file, and it read the file, and now it's making a plan, and we will soon see what the plan is. Okay, so sample says 250, that's correct. Number of controls. All right, so that's the plan. And then it asks us if we want to revise the plan. We will talk with the model about the plan a bit, because we want to get all the details right before it starts coding. And we'll ask how it plans to implement certain things. And once we are sure that it has the simulation design understood correctly, then we'll ask it to code it. So we will not start coding before we have the simulation done. If I start coding right away, I'm pretty sure that it doesn't get all the details right. And then the problem is that because there is an incorrect implementation already, it's more challenging to get the implementation fixed than it's to get the plan fixed and then the implementation based on the plan. So with 10,000 replications, that's what we have in the paper. And then we have X and Z. Then this important control, this is a suppression effect, that's right, from the paper. This is something that Claude 3.7 really struggled with to understand what important control is. But in this case, this is exactly right. Dependent variable R square 0.30. I guess that's what we say in the paper. And to approach is correct. This is correct. This is correct. And calculate bias. And then we have the visualization replicating the figure 4. All right. And then summary statistics. We didn't ask for that, but we can just have it. It doesn't make a difference. We will need to keep planning because there's a lot of details that the model is not writing here. So we need to ask it for example, let's make the plan more detailed. We ask it to make the plan more detailed because this is something that you have to specify. So this is the model from which we simulate. And you can see that there are correlations between x and the c variables, and they're all set to core xc. And then we have these effects from x, and c1 and c2 and c3 and how many c's we have are the same. And now we have the model to think a bit more, and single control. Yeah, so other controls C to C need to specify. The PDF doesn't detail their correlation. And now if we ask the model just to code this simulation, what it would do is that it codes with some reasonable values. For example, it probably would code that these C2 and C3 wouldn't have an effect, because that's kind of like a reasonable default. We will need to tell it to look hard at figure 3 and say that missing information can be found there. So look at figure 3, you can find this information there. All right, then I need to clarify for multiple PDF. It doesn't explicitly say what are correlations between the C variables. Okay. What are the correlation between X, C, and C? What are the effects? How exactly is the corresponding matrix equation structured? We will tell it that look at figure 3 and you can find the information there. And then we tell it that this is what you need to figure out based on the information presented in figure 3 and your reasoning. Do not fetch the code. Yeah, this is important because the model is so smart that it recognizes that we are actually publishing the code. We don't want it to retrieve the code. We just want to have the model go through the paper itself and try to figure it out. If the replicating a paper with AI is pretty pointless if you can just download the code from online. But we're trying to see if the AI tool can generate a good enough simulation that replicates this paper. So let's see if there's anything else. And while it's working, I can talk a bit more about these tools. So this tool is Claude Code 2.0, and it's a Visual Studio plugin. And what I'm using here is a paid, it's Claude Pro account. And I have an annual subscription. I pay about, maybe the normal price for annual subscription is $15 per month, but I got it for half the price. They had a campaign last winter, so I'm paying maybe something like $7 or $8 per month, and I can use this Claude Code pretty liberally. It has some limits, and I often run into those limits if I do something like use it extensively, and then the limit resets every 5 hours. But we can do this kind of thing pretty easily within the limits. And I think this is a no-brainer to buy, or this or a similar tool is a no-brainer for anyone who works with simulations now. All right, so let's see what it can deduce. So all controls correlate with each other to this at some correlation, the same value for all pairs. That's right. All controls have the same correlation with X. That's right. Is 1 calculated to make C1 impotent. All other controls have the same effect as X. So it could read this figure. So this is not a PDF figure, it's just a bitmap. And we could zoom in and see that it's just pixels. So the model is using reading the figure instead of reading the text in the figure. And then it does some matrix equation. And what values with core CCB set to? PDF doesn't specify this. It does specify it. So it specifies all correlation core XC, and we don't specify this part. So we can say that, are you sure that this is correct? Because it says that all correlations are X, C, not C, C. Let's see what it does, and then we'll tell that core CC doesn't exist. We only have core CX. Yeah, and now it's spotted the error that the correlation lines between C and X are labeled core XC. They all connect both X and Y. Well, that's not correlation between C variables. I see the arcs connect the C variables to each other labeled as all correlation CC in the margin area. The C variables like independent of each other, so it's not perfect yet, but it's very close to correct. So we will tell it that there is no core CC in the figure, but core it is XC should be used for all correlations. And then it asks if it has understood it correctly. This is correct, and as far as I remember. Let's see the plan, and then we don't put it to code yet because we want to discuss some technical details. By default, the model will make a simple implementation that doesn't use multi-core processing, and it's going to run a bit slowly. So I want to use parallel processing to speed it up so that we don't have to wait half an hour for the results to come in. Okay, let's verify that everything is correct. So that looks good. Yes, yes, yes. Okay. Yes. So that is the correct equation. Okay. Yeah. And then prolific, blue line. Yeah, so that's right. And then frugal is the red line. And then we want to keep on planning because we want to have it wants to create multiple R files, but this is a simple thing, so we'll just put it in one file. So we'll do that, and then I want to have multi-core processing, so we'll keep on planning. The plan is good, but I want minor changes. It's one R file. So we want to run parallel processing because my computer has 10 processor cores, if I remember correctly. So if I use all the cores with parallel programming, then this is going to be 10 times faster than without. And we'll ask it to update the code, so the plan. If we wanted to make this more fancy, we could ask it to used packages. Like there is a good package called SimDesign, and I can try that later. For now, it's almost certainly just going to do nested for loops to implement the different conditions. And let's see, yeah, so it says nested loops with parallelization, and this inner loop is 1000 replications, and this is future replicate or future apply. And then we will say that it's probably going to do future replicate because it's a bit simpler, and does it otherwise look good? So it's a good idea to review the plan before you ask it to code, and then it just generates the code after the plan has been approved. All right, that looks good. Yeah, we use ggplot actually in the paper, so it's gonna look probably almost identical. And yeah, and we auto accept, so we allow it to edit. And we can now open the side panel here, and the side panel will it'll show us a file that it generates. So all the files go here, and it creates a to-do list of what needs to be implemented. And how it works is that it goes to the to-do, it codes something, then it tests it, and then it codes the next step. So this is a multi-step process where it builds up the simulation step by step, and it'll take a little while, maybe a couple of minutes, for it to implement this entire process. And now it opened the file for us, and let's open it here. And now we don't, let's make that a bit smaller. So this is the file that it's generating, and it creates a very tidy R code. So this is a lot cleaner than what I do, and it's very well commented too. So how I sometimes do is that when I have an R file that I worked on myself, like the old-fashioned way, just type your analysis, I tell the AI to clean it up, and then it'll comment it, add this kind of nice separators and that kind of things. And now it says that it's completed. And let's see, there's functions, because this is a coding agent, it likes functions. And instead of, like, if a human was writing this, then they would just write the code instead of using functions. So there's grid correlation matrix and replication, and run simulation. Let's see, there is result is expand grid. So this is something that I would do. This is a simulation. This is a design matrix. So it's looping over the design matrix, and it taking the number of controls, the correlation, and then future replicate. This is the multi-core processing, and then it prints some kind of diagnostics, some kind of monitoring thing here. And it would take me quite a while to verify that this is actually correct. I'll just eyeball through it, and then data processing, then it creates the plot, and then it creates a summary statistics. All right, let's see how it works. So we can make this a bit bigger. And okay, so this sometimes happens, and then I can just copy paste the error here. And then I give the copy paste the error here. So, and then it fixes it for me. So because these models are stochastic, you never know how well the demo is gonna do. So sometimes it just, the last time I tried this, it produced me a simulation that worked, but it didn't produce the correct results. And now it produced me a simulation that looks like it's correct, but it didn't work. And we can just rerun it. And this is something that a human would do. Like you type your R code, you run it, and then you realize that it doesn't actually run, and then you fix the error. Okay, and then let's ensure that we have the most recent version open. So we're gonna reopen it, and we can tell it that run the code and ensure that it works. For testing, set the where does it store the number of replications? N reps to 100. And now it's going to ask us permissions to run code on the computer in a minute. And when there's like some security here, if you allow, so now it asks us the permission to run. And we reviewed this, that it doesn't do anything dangerous. And then we just say, you can run it how many times you want. So it's very unlikely that it writes something dangerous into the R script. But generally, you want to verify all the commands that the LLM works. LLM runs. There are some horror stories on the internet how someone lost a whole bunch of data when the LLM just deleted the code base. So it's reading it part by part, figuring out what's the problem. These tools are a lot better at generating code than fixing it. So it can fix its own errors, but typically fixing errors, it's a lot more time consuming than just generating new code. So now it's running, and if we want to see what is the input, we can, so this is the command, and then it produces some output. But I guess it produces the output only after it has completed the run. So that's the output, and it was able to run a bit. Here, all the red lines are something that it deletes, and the green lines are something that it adds. And drop equals false would be the correct thing to do here. Because if you want to retain things as matrices, then if you subset, if you take a submatrix that has one row or one column, then that automatically collapses to a vector unless you do the drop equals false in R. So I've been using this coding agent quite a lot, and particularly if you don't need to replicate exactly, then this is really, really useful, because if you just want to kind of like see if a technique works or not, then it doesn't really matter what the exact population parameters are in your simulation. So what you can do is just tell it that generate me a simulation that compares, for example, OLS and two-stage least squares. And it generates a simulation, and whether the simulation, the population model is correct or not, really doesn't make a difference as long as it is a population model. And this is how a human would also fix the code. So you run it piece by piece to see what the output is, and then when there is unexpected output, or when you assume something incorrectly, then you go and back and fix it, and you rerun the code. And this is exactly what the computer is doing now. So we can see already that there is a figure that it has been able to produce, and I don't know why these plots go to a PDF. And next we're going to run it ourselves with n equals 1000 and see if we get the correct result. So just to remind, we want to get something like that. And this is now set to have 1000 replications, and then we run it, and it's running. So when the number of controls gets bigger, then it always takes a bit more time to run the simulation. So the 30 controls is always, that's a ridiculously large number, but that's always the slowest. Almost done, and now we're done. And when we look at the figure here, and we can take a look at that, that's it doesn't look correct because the colors are incorrect here. And let's take a look at the figure 4. So the pattern of results is exactly correct. If we increase the number of replications to 10,000, then we probably get something very similar. Let's move it here so we can compare. So then we get something very similar to what we have in the paper, where all the observations are here in a single line, and these go down pretty smoothly. So that looks right. We can ask it to check the colors. Let's say that the original plot and the original plot was figure 4. So check the colors and line types. The error here is that now it's using red and blue for the number of controls, and then line type for the different different perspectives. So let's move that here and take a look at the code. So we can see here that the ggplot is the values here. Frugal is solid, prolific is dashed. It should be red and blue, which was the plan. And so you can see that the agent sometimes just deviates from the plan. What was the original plan for colors? And now it fixes that line type pattern is the number of controls. Color is the number of controls. Okay, and then we can rerun it and see what it produces us. So we are gonna rerun it. So this is the frugal red, prolific blue, and run. We could of course make this a bit fancier by having it to save the results and then plot from the saved results if we want to debug the plotting, but it doesn't run that long for the full simulation. All right, and there's still some randomness here, but this is almost certainly just because of the replication number is a bit smaller. These curves look almost exactly identical what we have in the paper. So there's some little weirdness also in the paper here with the 30K with the most number of controls, or 20 controls actually. And this is because when you have so many controls, you have the number of the multicollinearity is extremely high. So you get these weird outlier results, and those outlier results bias the results. Now we can do a couple of different things, and we could ask the model, for example, to now retrieve the original R file and then compare from OSF, or we could ask it to convert this to a different package, for example. And we still have 42% of the context remaining, so that's quite a lot. When the context gets full, then it kind of writes a summary because the memory of the model is full. Then it writes a summary of the discussion this far, and it starts to start from scratch with the summary instead of the full context what it has done this far. So let's ask it to verify this implementation against the code that is provided in the link. The article provides the OSF link to the code. Retrieve the code from the link and validate our implementation against the published implementation. So it can browse the net and retrieve your various things. And web retrieval requires permission, so we allow it to read it. And now it's looking for the R file. it's possible that it can't find it. So there might be robots.txt that prevents automatic crawling, for example. Okay, there is an API to OSF. I was not aware that that exists. So one cool thing about having these models code things for you is that now this is like it's running, it's retrieving, and it's using Python. Yes, we are okay with that. So you learn new things, but just by looking at what the model does. So now there's it found that extended R code for appendix, and R code for appendix likely contains the simulation code. Let me download it. Yes, we have it download, and then it can compare. Now it got the original code. I don't know. We could go here and see what the problem is by inspecting the code, what they're actually trying to do. But I've been using this quite a lot, so I trust that it gets this kind of correctly. So okay, so let's see what it said. Figure 4 in the paper action from varying R squared, simulation 1 appendix code, not varying number of controls. The original code varies R square. Yes, we do that, but that's not the correct file that it's looking at, because the reviewers for this paper asked us to do all kinds of things like, does it matter if R square varies, and we had an extended example. Yeah, the R code uses different variable names. Yeah, it's correct, and we replicated the wrong simulation. Okay, we are not gonna replicate the chasing R square. We have that in the OSF, but the point here was that you can ask it to retrieve files and compare. Now the final thing is that I don't like how this code looks. So if we can close that. So I don't like how this code looks. So it's a bit messy. It contains a lot of loops and stuff, and it's not something that a human would write. This is kind of like someone writing who is experienced in Python writing R code. So what I want to do now is to enter planning mode, and we're gonna ask it to implement this with the package. So implement the simulation with the SimDesign package. The model might know the SimDesign package, but I'm not sure about it. So it might need to retrieve information from the internet. Okay, let's see the plan. Let's make this a bit bigger. Generate and summarize phases, okay. Build in parallel processing, automatic result error handling. Okay, let's have it go. I think I have SimDesign installed, but it's good that it checks that I have it. It's probably going to write a new R file, because this is a substantial rewrite, and how the agent normally does is that if it does something that changes a lot of things, then it saves the old version for your reference. Okay, it produced it edited the same file, and it just made these functions. So there's generate, then there's analyze, and then there is a summarize, which calculates the bias values that we plot. And then now it's testing it. Yes. Okay, I hadn't installed it. So when I update R, then I always need to install everything. And if I haven't used the package for a while, then it needs to reinstall. And the model is now smart, so we told it that during the testing, reduce the number of applications to 100. And then now it runs it using the same seed for each condition. It's a bit questionable, because then if there's like one weird random number in one of the conditions, then it's possible that it's present in the other conditions. So you should generally use a stream random number generator if you want to do reproducible seeds, but it works. Like, this is a simple simulation. Yeah. All right, so it works. It ported our code to using a package, and yeah, it's pretty cool. So this is a game changer for me. So I can now, when I write a review, if there's like a claim that I don't buy, I can just tell the Claude Code that here's a claim about a method. Write the Monte Carlo simulation that tests this claim, and then it does it for me. And if then I review the code, if it supports the idea or if it refutes the idea, I can just put it in my review report. And also for writing demonstrations for students, just makes life a lot easier.